Okay, so basically we want to look at the cyclization of aldoses and ketones. Are you not supposed to be in that class though? Okay. So cyclization of aldoses and ketosis. Okay, so you already know your simple sugar. Your simple sugars are aldoses and ketoses. Okay, so basically this one belongs to the aldehyde family. Do you remember the aldehyde family? Aldehyde, good. Then the ketoses are the alkanals. Okay, alkanals. So what we want to look at is how they cyclize. Now, why do we need to study cyclization? It is because in real life, in physiological condition, that is, in the condition of the environment inside an organism, this some molecules don't exist as the way we draw them. So, for example, this is the structure of glucose. Glucose looks somewhat like this. It is a 6-carbon molecule. You know that thing, C6H12O6. So this is it here. This is the actual structure. This is called the Haworth convention or Haworth projection. 1, 2, 3, 4, 5, 6. So we have OH. We have OH here for glucose. OH here, OH here, H, OH, OH, and CH2OH. Then H here and H here. Now, so this is the way this guy exists, okay? But this is the open chain form of glucose. But inside us, inside the cell, which is called physiological condition, inside the cell, these molecules do not exist this way. It is just a small fragment that you are going to see in an open chain form. Most of it, about 80% of the entire glucose you see in your cell or in physiological condition, they exist cyclized, okay? So I'm going to show you how they cyclize. They exist in cyclic form, all right? So the form for glucose, I'm going to draw it, then now show you how it is formed. So the form in which it exists. Actually, this one I drew here is the actual cyclic form, okay? But the one I want to draw here is the one that, sorry, that one is called, this is called Fisher projection, sorry, Fisher projection. Is Haworth convention that we now draw that cyclize. So that Haworth convention is what I'm going to draw. But this is the way they exist. They exist in chair conformation. Sugars in your body exist in chair conformation in your cells. But we draw, the Haworth convention is for simplicity's sake and ease of drawing. Okay? So the way glucose actually exists is somewhat like this. So we have CH2OH. So actually, this is D-glucose and called alpha-D-glucose. Alpha because this carbon here is called the anomeric carbon. Okay, it's called the anomeric carbon because it's the carbon that actually engages in that cyclization process. Okay, and it is more oxidized than every other carbon here. If you count how many carbons we have here, 1, 2, 3, 4, 5, 6. Okay? How many H's do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. H12, O6. If you count the O's, there are also 6 O's there. But the point is that this carbon is the most oxidized. See how many oxygens are linked to it. The first oxygen here and the second oxygen. Hence, it is called anomeric. Okay? There are other reasons why it is called anomeric. But for now, just know that the anomeric carbon is more oxidized than every other carbon. Is that waves? Alright, so now when they cyclize, the process of cyclization is actually called intramolecular, I'm going to break it down, intramolecular hemiacetal cyclization. Now, cyclization becomes cyclic. Hemiacetal, hemi means curved or round too. Acetal, that is acetone. Is that okay? So meaning that it's having to do with aldehydes. Then intramolecular, that is within the same molecule that the cyclization takes place. Within the same molecule. You will understand. Just stick with me. You will know how to draw it by yourself, in fact. You just stick with me. I know the names may sound bemusing, but just stick. You are going to understand. It's very simple. Now, let me use first, when they cyclize, they form what is called a pyranose. Now, pyran is actually 6-carbon sugar. That's not pyran, 6 carbon sugar ring. 6 carbon ring. No, not carbon sugar ring. 6 carbon ring. Pyran knows the word O's now means sugar. So 6 carbon sugar ring. So if you see pyran, simply means 6 carbon ring. Then these ones, alkanals or ketoses, actually prefer furanose ring. Okay? So for the purpose of simplicity again, I'm going to be using hexoses. Okay, they are the ones that basically cyclize, and they are the ones that are abundant in physiological condition in your cell. All right. So furanose for ketoses, pyranose for that guy. Now, what are the aldehydes I'm going to be using? I'm going to be using glucose. This is glucose here. I'm going to also be using mannose and galactose. I'll show you the diagrams. Then we also use fructose. Okay? Yes, fructose is a ketone or an alkanal. Okay, but we don't call it alkanal. We call them ketones because they are sugars. They are simple sugars, and they have 6 carbons. They have the same formula, only that this one belongs to the alkanal family, while this one belongs to the aldehyde family. Now, let's use aldehyde as an example to show how they cyclize. I said when they cyclize, they form a pyranose, and this is a pyranose here. Pyranose simply means 6 rings, 6 edges. 1, 2, 3, 4, 5, 6. But because it's sugar, there's going to be an O here. This is pyranose, and this is furanose here. So this is pyran, exactly, or pyran, whichever way you pronounce it. Pyran and furan. So how does cyclization take place? The hemiacetal cyclization actually takes place when there is an attack of aldehyde by, notice OH group is called what? Alcohol, right? So when an alcohol attacks an aldehyde group, that is what we call hemiacetal attack. Hemiacetal is formed. So what happens is that an alcohol is going to attack an aldehyde in the following process. Keep in mind that the process is going to take place in a protic solvent. The protic solvent is a solvent that has proton to donate. And water is protic. Why? Because, when you ionize water, you get H++ OH. So it has proton to donate. So it takes place in a protic solvent. And our cells has water, so it can take place inside us. So that's one of the conditions for this cyclization to actually occur. The process is simply, let me first use a simple analogy that shows this is going to be the general formula for aldehyde is H here, aldehyde, okay? Then our alcohol is going to be ROH. Do you remember what's it called? Functional group? Do you understand organic chemistry well? Do you understand organic chemistry well? Okay, I'll teach you here. Now, like I was saying, so this is the basic structure for alcohol, and this is for aldehyde. So, in the Lewis diagram of this guy, drawing the octet structure, we're going to have that this guy has 8 electrons around it. So there will be 1, 2, 3, 4, 5, 6, 7, 8. Okay? Then for this guy, the same thing, 1, 2, 3, 4, 5, 6, 7, 8. Okay? So keeping in mind that this O is the center for the attack. Alright? So what happens first is that this guy, being more electronegative, oxygen, is able to, in the presence of a proton, okay, is able to abstract this bond to itself such that it now has 3 lone pairs. 3 lone pairs because there are 2 electrons in this bond. So there will be 3 lone pairs. 1, 2, 3, 4, 5, 6. So it now uses one of the lone pairs to attack this carbon. Immediately the attack takes place. This guy also is going to abstract this bond to itself. On the abstraction of that, this guy is also going to have 3 lone pairs. Then using one of that lone pairs again is going to abstract a particular proton that is present in its environment. Is that clear? So when that happens, then cyclization has occurred. Okay? So using this guy now, let me show you the exact thing, the exact way it forms. First, let me show you how to draw the cyclic form. The cyclic form is the one I want you to know first, okay? So I will draw the open chain form, you draw the cyclic form. But let me use this one to explain. Exactly. So I'll now give you another example. This is how to do it. You see this chain? You flip it in this direction. Flip it like this. Now, I won't be advising you to be drawing it, but I'll draw this first one when you flip, because you should be able to use your eyes to do it without touching it. But this is what I mean. Flip this is going to give you 1, 2, 3, 4, 5, 6. Double bond. O will be down here. H will be down here. Then the bonds between them like this. Okay. Then the last one, CH2OH will be down because if it's facing here, this one will be down, right? OH will also be down. Make sense? H2 is like H here and H here, right? Then this one will be at the top. Do you know? Do you get that? Okay, this structure is wrong. Okay, no, it's wrong. It's not wrong. This H here is at the top. If this thing bend like this structure H is at the top. OH here is at the top. And here, H is at the top. They'll all be down here. OH, H, OH. Good. So if you want to cyclize it, it's very simple. Draw your pyranos. For the ones I'm going to give you, it's just pyranos you need to draw. Okay? They are going to belong to this aldehyde family. So these pyranos represent 1, 2, 3. Each of these vertices, have you been taught skeletal structure? Each vertices represent a carbon. So this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. This is their numeric carbon. No, this is their numeric carbon, sorry. This fifth carbon is their numeric carbon. So it becomes the first one. So 1, 2, 3, 4, 5. You know it's remaining 1, 6. So you now draw a bond here and give this last one CH2OH. Make sense? Then on the vertices there, you now put a bond there. So to now know the direction, what students find out is to know the direction of these guys. For this guy, you can leave it last. You can do it last. Because it's the first carbon. Think of it as this first carbon. This next carbon here is going to be down here. This carbon here is on top. So if this one is down, H is up, right? Here, this OH is here. Here, this H is down. Here, OH is down. Here, and H is up. So with this, H will be here also. Now here, the position is, the position can change. You can put OH here, you are still correct. This is still glucose. You put OH at the top, it's still glucose. Only that they call one, this one is called alpha D glucose. The one where OH is on top and H is down is beta D glucose. Yes. Why is it called D glucose? D glucose is the glucose that this anomeric carbon, this is the carbon that is doing the attack. The carbon that is here has the OH to the right hand. So we call it D glucose. What's the D? The D means dextro-rotatory. Do you remember? The stereoisomerism that you did that can rotate plane polarized light. Okay. D glucose. Okay? D glucose. Alright. So now, given what you just understood, you are going to draw the cyclization of the ones I will draw on the board, okay? But then I will explain this during that time. So you draw for mannose. Now I want to draw mannose and galactose. They're actually called epimers. Those two, they are epimers. We also have allose and ultrose. They are also epimers. Why are they epimers? Is because you see that the structure looks exactly alike. So look at it here. For mannose, mannose looks something like this. 1, 2, 3, 4, 5, 6. H2OH. OH. 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 H. Okay? So looking at this, you see they look very much alike, right? But these ones are not epimers. Mannose is an epimer of galactose instead. So this structure is for mannose. It's also a sugar. It's also a simple sugar. Then this other one, 2, 3, 4, 5, 6. So CH2OH ending it. But in this case, we have OH group here and here. Then H here, H here, H here, OH here, OH here, H here, then double bond OH. Whenever the OH, this anomeric carbon, the OH is to the right. This is also D-galactose. This is what? And this one what? D manus, because this OH is also on this side. I flipped it. I put the OH here. This will be L manus. Think of L as left. The way I teach my students is D. You know when you want to write right hand, you first draw D. So when the major functional guy is on the right, the functional group is on the right, you call it D dextrorotatory. But there's another thing you have to know before that though. Okay, so try to draw the Pyranos form of these two. Okay? But let me explain. I said flip this thing, flip it this way, and redraw what you have here. So you will redraw what you have there in this conformation. Then draw a Pyranos like this, a 6-carbon ring, 5-carbon ring actually, that the 6th guy is an oxygen, like this. Knowing fully well that these first 5 are carbons. Then fix a carbon here, the last carbon, which is always CH2OH. You can put it at the back and put it in front. Okay? So once you draw this, the one that now matters, that students usually find hard, is the positioning of the OH and H's. Is that clear? Alright, let's do that. Do it. Yes, 42. Okay. So now show the mechanism of the reaction, the mechanism of the cyclization. This is the way it cyclizes, by the mechanism. This is the way it goes. So this guy wants to attack this guy. So it is going to cyclize in this way, such that it brings this 5th carbon, the anomeric carbon, as close as possible, or in close proximity as possible, to this O. So when it does that, remember that the O was the carbon was already attached to, the carbon was already attached to OH and H. Okay? So what it wants to do is that it wants to here, before we form this, remember that it was a double bond that was attached to this oxygen. So when this is formed, at this point, there are already 3 lone pairs on this guy. So it is that one of the 3 lone pairs that it uses to attack this guy, and after attacking this guy, it is now going to form, this guy is going to lose this proton, the bond with this proton, and another one of these is also going to be used to protonate the molecule, okay, such that it's going to abstract proton to itself, and then you can form this. So this is just the intermediate step I wanted to show you. Okay, that's the intermediate step. And so that'll be it for this video. Do well to subscribe to the channel. God bless you. So cyclize these ones and you can send me your answer on this WhatsApp number. So, and as well, I can send you other questions on many other hexoses for you to try on and cyclize. The next thing we'll talk about is mutual rotation of these things.